thank you, everyone, for being here. Yeah, I'm Cody Gunton. I'm on the ZK-EVM team at the Ethereum Foundation. This is a link to my slides, and this is a QR to my slides. There are some links in there that you might want to follow up on, so feel free to pull that down now if you're interested. Yeah. Seeing some action. Okay, cool. Yeah, so I originally was going to talk about something a little more narrow, but then I thought it's good to give more of an overview of the project. So we'll get to the question of specifications at the end and some progress I have there. But let's just start with what it is that we're doing and how we're going to do it. So I like this frame for what ZK-VMs do, which is that they let us leverage this, a certain asymmetry where you can have a network of very low power nodes checking the work of a bunch of very powerful nodes in that network. And they can do so with a small amount of data, okay? And so our application, of course, is Ethereum. We're interested in applying this paradigm to allow attesters to stay low-powered while allowing, at the same time, the network to scale, okay? So a priori, if you just did the normal thing, what you do is you re-execute all of the transactions at every block, and then if the number of transactions grows, then the requirements to do so also grow, right? You need more data, and you need more compute to do that. But what we'll do is we'll have the attesters run verifiers for these ZK proofs, and then we'll have the proofs be produced by these powerful entities who are kept in check by the attesters, and they're only going to need a small amount of data to do that work. So here's just a picture of what a virtual machine does. It's a silly picture maybe, but I don't know, pictures are nice. So it's just an implementation of a computer in software, yeah? Like you just write down the rules of a computer in your favorite programming language, and then you can say what that computer would do. If you actually built a machine that did it, that's a virtual machine. So the program runs inside, you have a physical machine with a virtual machine inside of it, and it can receive inputs and churn out outputs according to how a real computer would do. And the kind of extension of this diagram to the paradigm of ZK-VMs would be like this. I actually don't know if, oh, sorry. Can you see? Great, you can see my mouse. So it would look like, I'm going to try to talk into the microphone more, sorry. So yeah, we still have a virtual machine, which is this gray box, but it's running inside of another environment in the computer, which would be the ZK-VM prover, which sort of observes what the virtual machine is doing. But this bit of it's the same. We have inputs, program outputs in a virtual machine. It's just that the prover kind of watches what's happening and puts out a proof, right? And then to check that work, you take all of the inputs and outputs and you shove them into a verifier, and it makes a decision about whether the outputs actually came from the inputs based on the proof. And this is what the work of checking looks like. So it's slightly different. The in and the out may be different here. You'll see on the next slide what I'm talking about. So specializing it even more to our situation, we're going to have a ZK-VM prover. The virtual machines that are running inside of the prover could be other things, but they tend to be RISC-V virtual machines, right? RISC-V is an instruction set. It's an open source instruction set that is, I think, growing in popularity. And over the next 10 years, we'll see more and more in real computers. Already, you can buy RISC-V laptops. But it's an open standard, and we like that sort of thing. And it seems to work quite well. So then inside of that is yet another virtual machine, the Ethereum virtual machine. That's now the program, if we look back at this diagram here, right? This program right here. This is now another virtual machine, the EVM, which we know is the core engine of Ethereum. And so what we're going to do is we're going to have a prover observe the execution of the EVM inside of a RISC-V environment. And then it's going to transform the state of Ethereum given a block. And it's going to do so with this attestation, which is a proof. Okay. And I mean, there's nothing new in this here. You just take all of the inputs and outputs, except that here you actually only need some tree roots. You don't need the full state to do this verification. Sort of the magic of hashing and Merkle trees makes this possible. So this amount of data, it's just sort of a shadow of these little gray boxes here. It's a small amount of data. And you plug that in, and then the verifier, the attester node, can decide whether that was a valid state transition or not without having very much in the way of computational resources. And just to be clear, I'm not talking about replacing the EVM with RISC-V. That's sort of loosely related project. You would do that so that this step here could be more efficient, but it is not in any way required for what we're working on. That would be a much larger scope. So, yeah, and that's part of what we'd call lean execution. All right. So yeah, ZK-EVM, that's when you choose a ZK-VM and you choose an EVM implementation. That pair is a ZK-EVM. The E is for the Ethereum part, yeah? And there are lots of candidates. So these are some screen grabs from some talks that Justin has given, Justin Drake. So here is a table he maintains very diligently, very detailed table of the ZK-VMs that exist. He presented this at the event we had in Argentina in November, and also now he's tracking guest programs. So any row in this table and any row in this table, roughly speaking, comprises a ZK-EVM. And so we have a very large design space, even with stuff that's already built, to say nothing of optimizing each component. So yeah, here are some links to the some YouTube playlists if you want to watch the ETH Proofs calls or the talks that we gave in Argentina. All right, so how will we ship this? Well, we're going to do it in two phases. The first one is called optional proofs, and that is because, well, it's a very big change, and it's, if we're not careful, which we are very careful, it's dangerous. So we're going to launch it in an optional phase where we can get a lot of data, iron out bugs, see how the network performs, understand these provers very, very well. And the downside, well, it's not necessarily a downside, but this does not allow us to scale Ethereum because it's optional. Right? So if we did scale Ethereum with optional proofs, the nodes that do just only use the proofs would, or sorry, that don't only use the proofs that do re-execution, they would not be able to keep up with the chain at some point, and we would lose a big part of our economic security. So we're not going to do that. And then later on, we can make these mandatory once we're very confident in how this works, and then we can start to increase the gas limit. Okay, so how will we ship? That is how. It's in phases. We have an EIP for the optional proofs phase, AD25. And there's a link in my references. So this is kind of a skeleton last I looked. It's under construction. But there's a lot more in the specs repos, and I linked to the most recent stuff there, if you're curious. All right, so who is shipping this? Here is a list of stakeholders. We have the ZK-VM teams. We have existing core devs. We have some new guest programs, new core devs coming in to build something that's really ZK friendly. We have Justin Drake and the ETH Proofs team. I'm sorry, did somebody? Oh, okay. We have my team here, the ZK-VM team. We have the Snarkification team, which is working on, a lot of stuff, but for our context, formal verification, like very strong security tools for shipping this. We have the cryptography team, which is looking at the theoretical side of the cryptography. Panda Ops is going to build monitoring and build provers and work on the infra side of it. We have the RIG, Robust Incentives Group, working on the prover incentives, and we have some grantees also working on this. And so here is a lot of the decisions are made collectively on this Git organization, the ETH Act, Applied Cryptography Team. And you'll see in here a planning repo. There's also a link to that at the end. And there's quite a lot. Actually, I think there's, 25 repositories. And there's a lot going on here. And we have very robust discussions where a lot of people give their green check marks to, or don't, if they don't agree, to the initiatives that we propose. And we also just started this week, just 2 days ago, this breakout call for the AD25 optional proofs EIP. So on that call, I presented, one more slide. So here's another screen grab from our planning repo, that we have the plans broken down quite granularly into these projects. Each project has a group of many stakeholders, more than a dozen people in some cases, who are all responsible for shipping this and making sure that it's correct and aligned, and it's a very good upgrade for us. And so this is one way that the projects look. You can look here. You can even see I took this screenshot last night, and yesterday Kev, the lead of my team, merged our updates. So we're giving monthly updates. Somebody from each project will merge an update to show progress on the initiative. And I presented this on Wednesday. So this is a security-focused roadmap, and it's sort of temporal, but in not a very fuzzy way, but kind of a fuzzy way, because some of these things already have strict deadlines, like this. Well, not strict, but I mean proposed. We make requests for things. But they have deadlines that have been published, like this SoundCalc integration, and these proof security and size initiatives. Those requests, deadline requests from the security team, or not the security side, who maybe I didn't mention the security team on that one slide, but we have a security team who are also working with us, of course. But the cryptography team has published a blog post asking for these by certain times, whereas some of these are a little fuzzier. But we do have this target, which is Hegeta. So the fork after the current fork under construction, Glamsterdam. At that point, we want to be ready to launch optional proofs. We need to wait for Hegeta for this to be a reasonable thing to do, because there will be repricings in Hegeta that will allow the provers to keep up with the chain, to get rid of some sort of pathological, not really realistic use cases where proving is much harder than re-execution. So the prices are off for that. But yeah, a lot of what's on here is, like for me, the things that I work most closely on are the security of the ZK-EVMs, and there are a lot of testing initiatives that are just tiny little specks in this diagram, but there's a lot. Each of these bars has a lot behind it, and I just wanted to call that out because I really think about this whole security question very holistically, and what I'll talk about next is rather specific and formal to do with specifications, but that's just really one piece of the puzzle here. All right, so that's sort of the end of my overview. So now I want to just dig in a little bit to some of the specification initiatives and explain what it is that we need to do in terms of specifications and what progress we have now. Because I think that it's kind of a cool initiative we have. So we need to know, what are we putting in the protocol? ZK is a very interesting field. I started doing ZK in 2021, and I mean, the number of significant papers that have come out since then is pretty dramatic. I'd say that the pace of research is slowed, and the pace of it's become more of like an implementation-focused discipline, but there's a ton that's happened. And I mean, the ZK-VM teams have been very impressive in terms of what they've built. They have very good performance in these systems. And something that you sacrifice when you move fast is some of the, dotting your I's and crossing T's in terms of writing everything down. I mean, a specification usually, in the ideal world comes first, and then the implementation follows. And practice, this often is not how it works, and I think that's acceptable. But what we need to know now is what's been built. Is the cryptographic protocol that's actually built by a ZK-VM a real cryptographic protocol? Nobody has just built a ZK-VM using the papers. They took the Fry paper, implemented that exactly, and that's what's there. There are lots of optimizations at the protocol level, and it's a sort of like ship of Theseus. You change this, you change that. Somebody knew this was secure, somebody knew that was secure, and they didn't write it down. And now what you have doesn't really that closely resemble what's in a paper, unless you're an expert and you sit down and read it, which is what we need. So we need to write down what the proving systems actually are, that are what were intended, to be implemented. So we need to know that those proving systems are then secure. We need security proofs like you would have in a paper for the thing that's actually was intended to be implemented. And then we need to know that thing was actually what was implemented. So you need to then read the code somehow and make sure that that's what's there. And also, if you're implementing RISC-V machine to emulate, inside of your prover the EVM, then you need to know that RISC-V was executed correctly, or that you're actually doing a real computer and not a computer that just returns true all the time or something. Similarly for the EVM. So these are all things that need specifications. And let's talk a little bit about the steps towards these specifications. So we have a call. This is a link to a blog post from the research team asking for white papers this year, where they want something like an academic paper describing the proving systems. And not just the proving systems in a narrow sense, but in terms of how they use what are called continuations or recursion, the sort of macro proving system that composes a bunch of smaller pieces into something that can run on a cluster of 16 GPUs, can prove a bunch of chips, can compress the proof to something we want to send to Ethereum, and so on. It's fast to verify. There's a lot of, it's a big composite system, and we need to know exactly what that is. Okay, but so after we have that, so the purpose of that is so that the research team can read it, and other independent researchers can read this and understand what's there. And then next we have this cool initiative called Arclib, where we have the formally verified ZK-EVM initiative that is building this. The Specification team is running that initiative, and they are building this library that can allow you to write down these protocols that I just discussed in the white papers, but using the formal programming language called Lean, which forces you to be, very careful, and also opens up the possibility to taking the proofs that might be written down in these by these researchers and turning them into machine-derived formal proofs, where you use software to argue that that a statement is true, like that the proving system in say some spec built up from Arclib, a spec for concretely say the OpenVM prover, to know that that actually is a sound proving system. That's a precise statement with certain number of bits of security, and you can actually have machines make that proof. They'll take the statement and then reduce it to axioms that are checked eventually by people, a small number of axioms in the language. Okay, so then, so what about whether the implementation matches the intentions? Well, okay, you can take the white paper and then read the code, and that's a good, important thing to do. And then so we should do that, and we'll do that. But eventually, you can do something similar to this formal check that I described for Arclib, proving that the sort of model protocol is correct. Now you can think about taking the implementation, which maybe is in Rust or C++ or CUDA, and extracting that, like making a Lean, a piece of software that turns that into Lean, and then arguing that the Lean is equivalent. Okay, and then you have to trust the extractor, but I don't know, would you rather audit some kind of extractor thing, or would you rather audit the proving system? I mean, it's in everything, like we want as much security as we can, and that seems like a powerful approach as well. Okay, so then, yeah, what about the RISC-V? Well, there's already a spec for that in this formal description language called SAIL. And actually, I mean, we have progress on that. So even this was only this week, I think. The Nethermind security team has announced the formal verification of OpenVM, and they'd previously done SP1. So they are showing that there's a correct, like using machine-assisted proving that the, and I'm not super deep on the specifics here, so apologies if I am slightly off to those teams, but what I understand is that they show that the formal semantics in these formal specs are what are implemented in the OpenVM and SP1 provers using these machine-assisted systems. So this is very, I came in not as a skeptic, but as a sort of undecided person on formal verification, and I'm being convinced that it's effective, and that these, especially with AI tooling, like you can accelerate some of the stuff that doesn't really need an expert human to be doing it, and then let the expert human check the work and focus on what's important. So yeah, we see really significant progress already. Okay. Yeah, so something similar for the EVM. There are formal specifications of the EVM. There are several. I didn't call one out in particular because I don't know what the state of the art is there. The Snarkification team would know. But the same thing can happen. You can prove that an EVM implementation is in accordance with a formal specification. All right. So then in these last minutes, I'll talk about something I've been working on. So yeah, like I just said, AI can really accelerate some of this work. So there does not exist a formal written down specification of the prover that the Zisk team implements. And this is generally true. There's been some progress recently, but yeah, this is a mature prover that's been running on ETH proofs that has great performance, and so it seemed like a good target to see about trying to generate like a starter that could become a spec, right? So the idea is, can I take this complicated code and turn it into something that is not complicated, that then maybe somebody on that team could carefully read and say, yeah, that matches our intention. If we had started with a Python spec, maybe this is what it would have looked like. So we endorse this, and maybe they'll eventually maintain this spec, right? You can test, like this is executable. So it's a spec, but it's Python, so it does produce proofs, right? So I did this, and I tried to do this in as hands-off a way as I could, really. So I'm sort of designing like some agents that kind of check each other's work. It was not super hands-off. I mean, I did this kind of as like maybe a third of my time over 2 or 3 weeks. And I had to be very insistent upon certain very basic premises, I think. But it's getting to a place where I think it's time for a more manual tuning of this spec. And it works. It produces byte-identical proofs to the GPU prover of Zisk in several cases. So that's pretty convincing to me. It also, the verifier verifies real proofs. And I have some, when I change a byte, the verifier complains. So the Python verifier verifies real C++ proofs, and not just the sort of base proofs that come early in the pipeline for Zisk, but even the final proof, the one that would go to a tester network. It's called a VADCOP proof in their case, so it can verify those. But again, like I said, I've been hands-off. There may be some dragons kind of lurking where there's some, I don't think there's any return truths in there at this point, but yeah, I'm not ready to say that it's correct either. But I invite you all to look. I linked to it at the end as well. So this has been in a good place for a little while. And then yesterday I thought, well, all right, let's see if we can do lean too. So I made a lean verifier. And once again, it works. It verifies the proofs. This took about 3 hours. Claude Code doing its thing. And it didn't work automatically. I had to iterate on it over that time, but eventually it works. And again, I can break it, I can change a byte, it makes the proof fail. That's not convincing that it's secure. I might have just chosen the one byte that's sensitive, but I think that it's also not totally uncompelling. I think there's a good chance that this is a correct implementation of the verifier, or at least it's close. One caveat with this is missing the, so in Zisk, you take the really complicated RISC-V implementation, and you compile, that's written in a language called PIL2 that compiles to some binary expression. I'm not turning that into lean. I did turn that into Python in some cases, but it's kind of like not clear that that's the right thing to do. Do people prefer to read the Python implementation of it versus the PIL2? I'm not sure there's a readability difference. So we need something else for that part for the RISC-V implementation that's embedded in this. But in terms of the actual like Stark protocol, that logic is what is in the lean. And in lean, I only did the verifier. In Python, I did the prover as well. So yeah, I mean, maybe that'll become something. Maybe we can prove that this is equivalent to a Arclib spec, and then, we get more assurances. And yeah, another pretty interesting thing that happened is that Alex Hicks, who's the lead of the snarkification team, and is behind this verified ZK-EVM project, he used this. It's this prover called Aleph by Logical Intelligence. I don't know much about it, but it is. It's supposed to be designed for formal reasoning, as I understand. And he said, okay, I want to give it a pretty non-trivial statement that's relevant to us. So like our polynomial commitment schemes in these proving systems use the theory of error-correcting codes, and a key component of, or like an important lemma in that world is called the Polish-Spielman lemma. And he let this thing just cook for 8 hours, gave it $215, and it made a proof, and the proof is correct. So that's, if you trust the lean, then you look at somebody reads the proof statement, and you should think that it filled that in. So it can be that we can produce a very robust system of machine-assisted proofs of statements, like you get assurances about our software using these techniques. All right, well, I'm done a minute early. Here's my list of references. And yeah, thank you all for your attention.